So thank you to be here this morning. So in my talk, I will talk about excitements, challenges, but also misconceptions in paleobiology. And I think these come from different sources, from history, anthropocentrism, paleontology, geology, biology, chemistry, and the vocabulary we use to name things. I will try to address three topics: these misconceptions and challenges related to the traces of life, the limits of actualism, and the interpretation of the fossil record and evolution, if I have time. So there are several hypotheses regarding the origin of life, and most of them involve the presence of liquid water, minerals, organic chemistry, and some source of energy. So based on the element abundance in our galaxy, water and organic matter should be abundant, and people studying interstellar clouds, meteorites, or making experiments in the labs show that they actually are, which doesn't mean life is abundant in the universe. In the 18th century, Berzelius described organic chemistry as the chemistry of substances extracted from living beings, plants, animals, and fungi, that cannot be synthesized in the lab. That was called vitalism. There was a big frontier between the organic living world and the inorganic world. Then his student, Wöhler, a German doctor, succeeded in the synthesis of urea in his lab, and he wrote in a letter to Berzelius, he had to tell him that he can make urea without requiring kidneys or animals, be they human or dog. So that means since 1828, we know that organic is not necessarily biological, and organic chemistry is the chemistry of molecules, including at least one carbon-hydrogen bond. Well, recently and during this meeting, we heard a lot about a beautiful mission on a comet, the Rosetta mission, and recent studies have confirmed again, based on deuterium-hydrogen ratio, that the water of Earth's ocean has a ratio more similar to carbonaceous chondrite than to comets. Some Jupiter family comets didn't show really these results, but nitrogen isotope also show that comets are different from Earth's oceans and carbonaceous chondrites. That means comets didn't bring water to Earth's ocean. It's more parsimonious to think that carbonaceous chondrite did, and so they didn't bring organics on the early Earth. But still, we can hear in the press and in many talks that the Rosetta mission is great because it will solve the question of the origin of life. You can see it on the TV, on even the CNRS website, on different websites in English of ESA and NASA and some newspapers, even though on the websites of ESA it's really well underlined that the objective of Rosetta is to understand the origin and evolution of the solar system, which is really a great objective and a great mission. So I think some of it is due to selling the mission, but also probably some vitalism is still staying in some of our minds. And this is not only the example. It's not only related to the Rosetta mission. So moving to another topic, the rocks. So this is part of geology. Rocks are archives of Earth and life history, and they can help us to understand what happened to Earth since its formation to today. This is a geological timescale that Stefan Mojdic explained yesterday. And we can try to reconstruct the history of Earth and life thanks to traces preserved in rocks. Unfortunately, not everything gets preserved. Rocks can be destroyed by different geological processes like erosion along the ocean, or by rivers, or by wind, mountain building that are due to collision of plate tectonics. And these processes, unfortunately, erase big chunks of rocks and big chunks of Earth and life history. Same thing for life. The traces of life that are in these rocks that have been erased, of course, they also disappear. But even if they do not all forms of life that exist today have the same chance to get preserved. It depends on the physical-chemical conditions of the environment where they are preserved, but also on their original properties. For example, these guys have mineralized skeleton, can be a big dinosaur or microscopic unicellular organisms. They might get better preserved in some conditions than these soft animals or plants or prokaryotes. So again, the story that we can reconstruct is from pieces of puzzles that are really rare. Fossilization is a rare phenomenon. It's also a complex process. Fossilization can also be a fast process. It doesn't take 10,000 years to make a fossil. That's what I learned when I was in school. But still, it's exceptional in life's history. So, despite all these fragments, we can try to reconstruct Earth and life history, and we know from different elements, and we heard also Stefan talked about that yesterday, that Earth was inhabitable before 4.3 billion years ago, has been habitable since then, and we have traces of life showing that life diversified at least by 3.5 billion years ago. That means it's older than that. But again, the story is fragmented. So when we look for traces of life in very old rock record, we can use 4 kinds of tools. We can look at biosedimentary structures, which indicate interactions between microbes and minerals, such as stromatolites here. This is a picture from Curie. We can also look at microfossils that can be preserved as organic compressions, or they can be mold, mineral cast of cells. We can look at isotopic fractionation of elements that life uses, and this will indicate the evolution of metabolism. Homochirality is also a signature of life, but maybe difficult to preserve. And finally, we can use molecular fossils, such as lipids and pigments, that will tell you something about the evolution of biosynthetic pathways and sometimes even of particular clades. But there are many challenges related to these traces of life. We already talked about the incompleteness of the rock and fossil record. The geological context is also very important to understand. Depending on the physico-chemical conditions where these traces are preserved, we get different results and different communities. For example, here you have 2 examples of microbial mats, one living on a beach on the North Sea, and one in a hot spring in the Yellowstone National Park. These will get preserved in different ways and leave different traces, so it's important to understand this context. Other phenomena like metamorphism, which is increased pressure and temperature due to piling of rocks on top of each other, or due to compressions during mountain buildings, for example, can erase, transform, alter, or erase biological properties. Here you see examples of 3 cells, 3 fossil cells. You see their age here, and you see the color change because more you cook them with metamorphism, more they lose volatile and they will be relatively enriched in carbon. If you continue the process, you can add graphite, pure carbon. Another challenge is the contamination. Once you study trace of life, a microfossil, for example, you have to prove that it is in the rock, not a contaminant. So you cut the rock in slices, you look in the thin section, you see it in the rock. Okay, it's in the rock, but it's not enough. It doesn't prove that it has the same age as the rock. And actually, what we date is the rock and not the fossil. So this is an important point. We have to prove the syngenicity of these fossils. So again, we can look at the distribution of fossils in the rock. We can look if they are flattened parallel to the layers, to the bedding, the layers of the rocks. So that means they were incorporated in the same time as sedimentation. We can look at the maturity of these organic walls with Raman spectroscopy and see if it's compatible with the thermal history of the rock. And this will help us to prove syngenicity. But still, we know we have to prove that it's really biological in nature. And there we have another challenge. We have many abiotic processes that can mimic life morphologies and chemistries. For example, when we use carbon isotope fractionation as a sign of life, we can have a range of values. You probably cannot see from far away, but it doesn't matter. We have a large range of values depending on the metabolism that uses this carbon. But you will also have a range of abiotic chemical reactions that can also fractionate carbon without life involved. So again, to discriminate, you need to understand the geological context. Minerals can auto-assemble and take complex shapes, filamentous shapes, or make little silica spheres that could look like life, but these are pseudofossils. This is a famous one in a meteorite. And organic matter can migrate around minerals and also form pseudofossils. This organic matter could be biological or not, but the shape, the morphology, is not a fossil. And then finally, when we find a fossil that's in the rock, the same age of the rock and biological in origin, we still have to interpret what kind of life it is. And this can lead us to other challenges. So a paper that was mentioned several times during this conference is a recent paper describing possible biogenic carbon in 4.1 billion-year-old rocks, zircons, minerals. So these zircons are well dated. The author described the presence of carbonaceous carbon inclusions in these minerals, and they measure carbon isotopic fractionation with a value of minus 24 per mil, which is consistent with a biogenic origin and may evidence the terrestrial biosphere 4.1 billion years ago. Sorry. But if you heard what I said so far, you know that the presence of organics is not a biosignature in itself. Carbon isotopic fractionation is not a biosignature in itself. And Raman spectroscopy can prove syngenicity, but not biogenicity. And in this case, this is the spectra from this paper. And if you look here, this spectra is not typical of a graphite included in zircons that has crystallized at 650 degrees Celsius, but it's more typical of less mature organics. So this spectra doesn't prove the syngenicity of carbonaceous matter. So you see that it can be really complex to prove that you have a trace of life, and you really need a combination of analysis and approaches to be sure. So let's say that we have fossils that we are sure they are biological in origin. You have all kinds of morphologies, all kinds of preservation and ages, but you still have a big challenge. What kind of life is this? And here we have other problems. I already talked about the processes of fossilization that can give different results. You see here the same species preserved in a silica-rich rock in 3 dimensions, or in the fine-grained rocks flattened in 2 dimensions. So this is the same taxa, but it's not obvious at first sight. Another problem is the fact that a same species can have different morphologies depending on its life stages. This is a dinoflagellate, so a recent protist. And you see here the vegetative cell and here the cyst, and it looks quite different. If you can culture them in the modern world, you can know that this is from the same species, but when you find that in the sediment record, it's difficult to know. We also have problems with convergence of morphology and chemistry. For example, here you have a picture of fruiting bodies of eukaryotes and bacteria, and at first sight they look the same. Another big challenge is trying to relate fossils to modern life. We don't know everything that exists, and we don't know everything about everything we know already about the modern diversity. So there is a lot of things we don't know, and it's difficult to sometimes relate fossils to modern life. And sometimes we should not try, because fossils may document extinct clades that have no modern representatives. And related to this problem, the stem or crown problem can be also tricky for paleobiology. So this stem crown problem is related to a common confusion between what is a first common ancestor and a last or most recent common ancestor. So I will try to explain. If you have a clade, a group of species, the modern living relatives and their ancestor to their most recent common ancestor is part of the crown group. And the first common ancestor of this whole group plus the clades that are extinct now, and they are between the first common ancestor and this most recent common ancestor, are called stem groups. So when you have a fossil, it's sometimes difficult to place it in a crown group or in a stem group, because the fossil don't preserve all the characteristics of the living organism. These notions of first and last common ancestor can be applied at different scales in the phylogenetic trees. For example, this is a tree of life. The three domains of life are here. They have a last common ancestor called Luca, but Luca is not the first common ancestor, it's not even the first cell, it's only the most recent common ancestor of the three domains of life, and this can sometimes lead to some confusions. You can also look at these notions within a domain, within a group of organisms. For example, within the domain Eukarya, you have different groups. You have also animals, and within animals, you have arthropods, which today includes insects, crustaceans, and other creatures. Within this whole group, you have the crown group arthropods, the living ones, plus their ancestor to a common ancestor, the last common ancestor of arthropods. But before that, you also have many lineages that are extinct now. They show some characteristics of the modern arthropods, but not all of them. And they are stem group arthropods. This is the first common ancestor of the whole arthropods, and it's link all these in the same group. They are more similar to each other than with other groups, like some nematodes, for example. So why am I talking about that? Well, this notion can be confusing and difficult. So when we try to place the fossils along the record, the geological timescales, and more we go back in time, less the fossils preserve enough characters to be able to identify them. So you have here the geological timescale and different kinds of traces of life. If we look at the domain Eukarya, I just talked about animals that are somewhere here, appear about 600 million years ago. In the domain Eukarya, we have a minimum age for the last common ancestor of eukaryotes around 1.2 billion years ago, based on a fossil that looks like a red algae. This is a minimum age. It's very possible that Lika is older than that. And Lika, the last common ancestor of eukaryotes, is not the first eukaryotes. It's not the origin of the domain of eukaryotes, which could be much older. It could be even appearing in the Archean. We don't know. Same thing for, oops, I have to hurry. For prokaryotes, Archean bacteria, we have traces that track them back to the Archean. But we don't know if some of these traces relate to crown group Archean bacteria, or if they could be stem groups. And then that means Luca is anyway older, and then Luca is not the first forms of life, so of course the origin of life is older than that. I will try to speed up. I just want to say a few words about the limits of actualism. Actualism is a principle that's used a lot in geology. The present is the key to the past. If you look at these shapes on the sand caused by the waves, you can find these sedimentary structure preserved in very old rocks, and you know that you are on a beach 2 billion years ago or 3.2 billion years ago. This is really important to understand the geological context where you try to find traces of life. We try to apply this principle to trace other traces of life. This is an image from Purie, from a book edited by Muriel. Different kinds of metabolism exist, and prokaryotes especially are champions in using all kinds of energy sources. They can use light, they can use organic matter, they can produce methane. And to track this metabolism back in time, we try to look at isotopic fractionation of nitrogen, sulfur, iron, the production of oxygen, or the production of methane. And we can track them back quite far in the rock record. However, we compare this signature to the modern signature that modern metabolism leave today in present environment, but we don't know if early members of these clades had exactly the same pathway, left exactly the same signature, and we don't know before Luca if early metabolism could leave similar signature that we could confuse with modern metabolism. So this is again a limitation of actualism. Another big limitation that Antonio mentioned yesterday is the fact that often people extrapolate the conditions of life of Luca to the conditions of the origin of life, and we should not do that. It's not need to be the same. The conditions that we try to reconstruct for the early Earth are global conditions, and of course they do not need to correspond to the conditions for the origin of life that probably appear in a micro environment. So studying extremophile is really interesting because it tells us about the limits of life, the diversity of ecological niches that life have colonized. It permits to enlarge the concept of habitability, but we should not forget that these are modern life. They are secondarily adapted to the conditions. This does not represent the conditions of the origin of life. And studying these environments is interesting, but they are not perfect analogues of early Earth or extraterrestrial environments. A last word about the fossil record and evolution, but I think Puri will talk more about that. So this is, again, the tree of life with time. I talked already about confusion between first and last common ancestor. I think Puri probably will talk about being evolved and being complex, so we'll not talk about that. We tend to reconstruct the history of life through time, and so this gives a false impression of direction, like Antonio mentioned earlier. But of course, there is no direction to evolution. This is just a succession of random events plus contingency. Not everything is possible in any conditions, and natural selection and exchange of genetic materials. And finally, evolution is a process that makes sense, but there is no sense to evolution. This is very different from the meaning of life, which is a personal decision, has nothing to do with science. So, last word, I talked about excitement in the beginning, and here it is. I think this is exciting. This is a cell that's 1.5 billion years old, and when you see that under your microscope, it's just amazing that it's still preserved, considering everything I just said. Paleobiology is great. It can provide, with fossils and other traces, minimum ages for the evolution of stem and crown groups, of biological innovations, including early metabolisms, ecological interactions, diversification, branching events, extension, extinct clades that have no living relatives, intermediate steps in evolution. It can calibrate molecular clocks when we can identify these traces. It may document the record of the evolution of life before the point where molecular clocks can go, because they are based on genomes of modern organisms, although we heard a little bit a tentative of studying evolution before Luca. They required a combination of disciplines to study, and I think the methods and challenges linked to paleobiology are also relevant to astrobiology, especially when we try to detect life on other planets or moons, and we try to understand habitability. And I would like to thank you for your patience. I think astrobiology is great. It's a big mixture of misconceptions, but we are here together to destroy them. And please point to me my misconceptions, because I have also misconceptions. Thank you.